So this is Pure 2, chapter 9.9. Moving on, in differentiation chapter, we are done sort of with all the differentiation skills. You've learned about differentiate exponential logarithms. You've known how to differentiate sine, cos, tan, trig. You've learned the three main rules that sort of rule the differentiation, known as chain, product, and quotient rule. Okay, I'm not going through all of them, just a quick reminder of what we've done with that. And then we've also learned how to differentiate parametrically. What else have we done? I can't remember now. Parametrically, and there's something else I should be recalling, but I'm not. Parametric and implicit differentiation. That's it. That's the last lesson. Implicit differentiation, where we slap a dy by dx if the variable that we're differentiating with respect to is not x, then we slap angrily with a dy by dx because that's more work. More work means more anger. Right. But today, what we're learning is about using second derivative. So, all the skills you've learned about differentiation is complementing with what you need to do. So it is not a new skill, but it's something more definition you have to remember. So this is a continuous lesson from last year where you remember about increasing and decreasing function. So increasing, decreasing function. Now, before we remember this, so a quick recap. Okay, so recap in year 1. So recap in year 12, year 12 recap. So if it's an increasing function, okay, if a question tells you increasing function, what's the definition of it? It means dy by dx is greater than 0. If it's decreasing, okay, you should know this, then dy by dx should be less than 0. If I want to test let's say a stationary point means dy by dx equals 0. If I want to verify the nature, okay, verify, is it max? If it's a maximum stationary point, then the second derivative should be less than 0. A minimum stationary point will be a second derivative greater than 0. So these are all the definitions you've learned in year 12 about derivative. Okay, so we're building up on this repertoire. We're going to build up on this one, apart from these 1, 2, 3, 4, 5 key points. Right, so notes. We can use second derivative to determine if a curve is concave or convex, okay, on a given domain, informally bending one way or the other. If, okay, the curve bend like this, okay, is that you're bending down to pick up something, then this is concave. If you are, I don't know what to describe this one, okay, going up positive direction is convex. So what we can look at this is one by one. If we draw a lot of, I call it gradient tangent lines, okay, tangents, these are a lot of tangent lines, okay. You can see the tangents, okay, these tangents, the gradient, okay, the gradient is decreasing. Well, why? Because you can look at this gradient. It's very positive. If you think about the gradient, very steep, okay? Slowly, gradually, we are moving to a more flat line. Means the gradient is going from very positive towards 0, so it's decreasing. On the other hand, this one, you can see the gradient is increasing. The gradient is increasing. Starting from 0 all the way up, gradually, you're going up but more positive towards infinity. So this is the convex and concave. In terms of the technical definition, we call f of x the gradient, and sorry, not the function itself is concave when, now key point, when the second derivative is less than or equal 0. Okay, concave. So we can build up on that one. So concave, concave means second derivative is less than or equal 0. Convex curve, okay, convex curve means second derivative is greater or equal 0. Now, the way you can remember these two is, that's how I remember it, okay, a bit cheesy, a bit lame, but cave, okay, to remember the sign, cave, only negative people hide in a cave because they are so negative, they should be locked in a cave. So that's how I remember it. If it's negative, second derivative less than 0 means negative. Negative people live in a cave, therefore concave. All right, so that's why they hide in a cave. And if you're negative as well, you should be locking yourself in a cave. all right, known as your bedroom. You shouldn't be coming out and spread your negativity. We don't need that. Okay, the world should be more positive people spreading about positivity. Right. Okay. Next. Now, what about the point where they overlap? Not all function is fully concave or convex. There will be a point on the curve where it's a transition period between a concave to convex or convex to concave. This point is known as the point of inflection. Now, point of inflection is like this. Let's say if you have a cubic graph. Okay, this is the point of concave. Let me show you. So this point, it's point of concave, point of inflection. Now you can see why, because this part of the graph is, if you look at the graph, it's concave. If you compare with the concave curve, it's bending down, okay? Where on the other side, let me bring a different highlighting color. This part is convex. So not all curve has a transition point between concave and convex. So then this is, point of inflection. So to show a point of inflection, okay, to show that sign, first of all, to show the sign of second derivative changes. So I'll build up from this point. Now for this one, you need to sub a value of x before the point, and then another point after point, another x value, actually, another x value. So it's before and after. You show a point before and after. Let's say this point of inflection is x equals to 1, 0. Then what you need to do is to show a point of inflection. You need to show, let's say you want to sub in x equal 0, just before 0 will be negative 0.01 and x equals 0.01. You need to show that f dash x, the sign changes. Well, why would the sign change? Because before that point of inflection is concave. Concave means the second derivative should be less than equal 0. That means when you sub in negative 0.01 before the point, the second derivative should be less than equal 0. Whereas when you sub in the 0.01 after the point of inflection, your second derivative should be greater than 0. So that shows the change in sign. Okay, if the sign doesn't change, it means it's not a point of inflection. Okay. To find out coordinates, you just simply do second derivative equals 0. Right? So let's see how we can look at an example and go for example together. Example, find an interval on which the function f of x equals x cubed plus 4x plus 3 is concave. So in this function, okay, the whole function, only part of it is concave. We need to find an interval where it is concave. So concave means, okay, so concave means the second derivative of f of x is concave, cave, negativity. We don't need it, it's negative people only. So it's less than equal 0. So we sub it, so we find the first derivative, differentiate once, 3x squared plus 4. Second derivative, differentiate again, 6x. Right? So concave means 6x has to be less than equal 0. Divide 6 over x less than 0 equals 0. That means the part where x less than equal 0 is concave. Okay, so that's the part. Now here I'll show you the graph, for example, that is the x cubed plus 4x plus 3, y equals that line in here. When x is 0, when x equals 0 means, let me actually drop this graph onto the whiteboard. So let me crop this. Where was it? Yeah. Okay. Right. So here's a graph. It's massive. Let me make it a bit smaller. Okay. Right. So when x is 0, when x equals 0 means that line here. Whoops. I don't want to rub it off. X equals this line here. Okay. If you look at the graph that's less than equal 0, it means this part of the graph. Now you can see the gradient is actually decreasing, even though quite gradually and quite marginally, it's quite small. The decrease is quite small. You can see from here, it's being very, very positive. These gradient lines, if I draw tangents on these lines, you can see very, very positive, but slowly and surely it's getting less and less deep. So that part is concave. And this part after the line, okay, after the line, let me change the highlighter color. You can see the line is getting steeper and steeper again. So this part of the graph is known as convex. So that's why we can work out which part of the graph is concave by using second derivative less than equal 0. That's concave, right? So that's an easier part to ask you which part of the graph is concave or convex. Next example, we look at slightly different question. Well, this time we will show that a particular part of the graph is convex. Now I want to show that this convex. Now this different to the previous question, even though they look quite similar in terms of wording. This one is find the interval on which the part is concave. This one is show it is convex. Show is convex means this is the conclusion. It means you can't use a conclusion. Okay, you can't use it. Okay, so you have to prove it. Okay, so you can't use it. So even though we know, okay, so we know convex means second derivative is greater or equal 0, we can't use it. We have to prove it. Okay, so let's see how we can do it. Well, to find second derivative, let's differentiate first. Differentiate first derivative. Differentiate e to the power of 2x to e to the power of x plus x squared is 2x. Second derivative, okay, differentiate again for e to the power of 2x plus 2. Now we just have to show this greater equal 0. Okay, so because e to the power of 2x must be greater than 0, well, that's the definition. Well, if you don't know why, think about the e to the power of 2x graph. E to the power of 2x graph like this. That's e to the power of 2x graph. This always above the x-axis, so it's always greater than 0. This effect, okay? There's not a conclusion, nothing. This is like 1 is always greater than 0. You know, 0.1 is always greater than 0. 1 plus 1 is always 2. This is mathematical fact. So, because e to the power of 2x greater than 0, if you multiply by 4 and plus 2, that's definitely greater than 0 as well. So therefore, okay, and therefore, f of x equals e to the power of 2x plus x squared is always positive. Therefore, it is convex. Okay, for all values of x. So that's slightly different type of question where it asks you backwards. Okay, so for it's convex. Okay, it's like approval for positivity. This guy is positive. You get a stamp of convex. Well done. Imagine tell it to a primary kid. Oh, being very positive. Let me give you a stamp. And a stamp is not nothing like nice, a star or anything. Okay, it's a convex graph. The kid will be looking at you, wondering what the hell is going on with this guy. It's weird. Next one, example. Using second derivative. Example, the curve has equation y equals x cubed minus 2x squared minus 4x plus 5. Show that C is concave. Okay, again, show that this is concave. So we can't use it again. It is a conclusion. So what we need to do is we first find the first derivative. So 3x squared minus 4x minus 4. Do the second derivative, 6x minus 4. Now, concave between the interval minus 2, 0. So when x equals minus 2, second derivative, when you sub into that 6 times 2 minus 4, that's, or minus 2, so it's 6 times minus 2, so it's 6 times minus 2, yep, I was thinking, why is it positive? Because concave should be negative, okay? Cave, negative, so minus 16, so less than 0. When x equals 0, sub in 0 in there, 6 times 0 minus 4, that's minus 4. So it's less than or equal 0. So that's less than or equal 0. So therefore, f of x is concave between minus 2 and 0. Now, if you haven't seen this square bracket before, okay, this square bracket, it means minus 2 less than or equal x less than 0. That means x is between 0 and minus 2. Okay, you'll actually use this for chapter 10 about numerical method as well. But for now, yeah. By the way, square bracket and curly and a round bracket actually means different thing. If you're interested, if I say minus 2, 0, like this means we're not including 0. A curly bracket means we're not including, and not curly, a round bracket means we're not including. Whereas if we, let's say, if we have, yeah, this one, minus 2, 0, this means minus 2 less than x less than equal 0. But, you know, it's not a big deal, but we usually write interval in this way. Okay. Right, next one. What about 1 and 3? So let's sub in when x equals 1. The second derivative of 1, we sub in 1 in there, we get 2. That's greater equal 0. When we sub in 3, when x equals 3, 6 times 3 minus 4, that's 14, greater equal 0. Therefore, f of x is convex between 1 and 3. So why can you just substitute 1 and 3? What about the middle values? How do you ensure that middle values are also convex? Well, that's a good question if you do think of that. The reason we know if we sub in minus 2 and 0, that's concave, and sub in 1 and 3, just the two n values that are convex or concave, and we can conclude the middle numbers are also, you know, the same as convex or concave, is because 6x minus 4 is a straight line. Okay, it means it's a linear progression. So when you sub in x equals minus 2, so the numbers only go in one direction. And unlike quadratic, you could do a U-turn, okay, cheeky, but a straight line, 6x minus 4, is if minus 2 works and 0 works, all the numbers between also works. Right. Next one. Find the coordinates of the point of inflection. So we have to do two things in here. First of all, we have to sub in second derivative equals 0, because that's what point of inflection means, but we'll also need to verify if that's a point of inflection. So to find a point, so let's find the point of inflection, which we do second derivative equals 0. So we'll do that second derivative. We know 6x minus 4 equals 0. So do the 4 divided by 6, that's 2/3. Okay, so when we have 2/3, we need to also find the y coordinates. So to find the y coordinates, we need to sub into the y equation. Okay, so y equation. So y equals to 2/3 cubed minus 2 times 2/3 squared minus 4 times 2/3 plus 5. Put in a calculator or use a super mental maths like what I do when I think I'm just born with it. 47 over 27, you know, mental maths. So point of inflection is, it looks like 2/3 and 47 over 27. However, you also need to verify the point of inflection. Is that really a point of inflection? You have to verify that. Okay, to verify it, you need to sub x equal. So just before the point, 2/3. So 2/3, if you think about decimal, is 0.667 or 0.67. You can sub in. So if it's 0.67, we can sub in a 0.66 and 0.68. Okay, sub in 0.66 and x equals 0.68 into the second derivative. Because we want to show the second derivative change the sign before and after the point of inflection. So second derivative of 0.6x is, let me use my mental maths, be right back. The second derivative of 0.66 is you sub into the second derivative, so 0.6 times 0.66 minus 4. Mental maths, negative 0.04. And then, okay, do the 0.68. 6 times 0.68 minus 4. 6 times 0.68. Okay, yes. 0.08. Okay. If you can't do mental maths like I do, okay, I forgive you. You can use a calculator. But you can see the sign changes in here. The second derivative signs change. Therefore, x equals 2/3 is a point of inflection. Now you need to verify that. You do need to verify that. So therefore, the ultimate point is 2/3, 47 over 27. You might be given more than 1 point, so you have to decide which one is the point of inflection. So by doing before and after, okay, then you can check if the sign changes. All right. Right. Next one. Oh, is that it? Yep. Okay. So that's the end of lesson. There's no practice question for this lesson because you can do lots of them in the textbook or the exercise. Okay, so that's the end of the video. Thank you.